of REMENA Gathering event, and thank you for joining us. Sorry, 1 second, I will share my screen.
Do you want me to start the presentation, Manel?
1 second, sir. Please make me host so I can share my screen.
Okay.
Sorry, sir. So welcome again to the second day of REMENA Gathering. I hope you will truly enjoy today's session. I'm very excited about the discussion we will get to have today with our guest speaker. And as we announced before, we have 3 professional speakers who will be sharing their knowledge with us on different topics. Our first speaker is Michel Caro. Thank you, sir, for accepting the invitation and being with us today. It's such an honor to have you. So before starting, I would like to introduce Mr. Michel briefly. Dr. Michel is actually the director of hybrid power at Hatch. He is a specialist in energy with a PhD from MIT and a postdoctorate from Boston University with more than 32 years of experience in energy. He has expertise in the development of many energy projects such as hybrid power, microgrid, and hydroelectricity, biomass cogeneration, and many others. Uh, Dr. Michel has also expertise in managing multidisciplinary team for innovative projects delivered in more than 20 countries. Uh, Today, Dr. Michel Caro will be talking about green hydrogen application and integration with renewable energy. So, sir, I'll let the stage for you, and thanks again for being with us here.
Okay. Thank you very much. Let me share my presentation and let me know if you see it.
Yes, it's clear.
Okay. Very good. Welcome everybody to the second day of the conference. Good afternoon, good morning, bonjour tout le monde. I'm based in Montreal, very happy to participate to this conference with all of you. Today, I'd like to present about green hydrogen applications and also its integration with renewable power. And so I'll talk about green fuel, hydrogen trucks, and also combining renewables and hydrogen to integrate more renewables on the grid. So just a word on Hatch. Hatch, my company, is a private company. It's a global company across the world with 100 years of roots of projects in more than 150 countries. We have offices throughout the globe, from North America, Canada, US, and all the Latin America, up to Chile. We have offices in South Africa and in Europe, India, China, and Australia, to name just a few. We are focused on doing engineering projects in 3 sectors: mine and metals, infrastructures, and energy. And under energy, we do everything from oil and gas to thermal power to renewable power, which includes wind and solar, hydropower, and also we do nuclear. And so on that, I would like to introduce the subject of hydrogen. The following chart shows the value chain of hydrogen from left to right. So the hydrogen can be produced in many different forms, different ways, using either renewable power or nuclear, which would be green energy or non-emitting energy. It could also be produced from biomass, coal, gas, oil, and it leads to different pathways from left to right of this chart. We'll be focusing on electrolysis, where the electricity can come from renewable power, wind and solar in particular, and then the hydrogen can be stored and transported through different means, ship, train, or pipelines. And for applications such as gas turbine and fuel cell, iron ore, refining, ammonia, methanol production from hydrogen. So let me show you a few examples of projects that we have delivered that are in operation. It gives a sense of what's been done versus what's coming. So this plant here is a 20 megawatt electrolyzer PEM that is in operation since October 2020. At that time, it was the largest in the world. It's still the largest PEM electrolyzer implemented in the world. But China just implemented a 130 megawatt alkaline electrolyzer just late last year. So this project, as you can see on the diagram, the electrolyzer building is a small square at the bottom of the screen. It's producing hydrogen, which is stored into gas storage, and it can be liquefied to the LH2 storage, the sphere that you see, which store the hydrogen in a form of liquid. This project can produce 3,000 tons of hydrogen per year. It is an expansion from steam methane reforming, which we see at the upper side of the screen, that already produce hydrogen using natural gas. So this green expansion of the plant is a great innovation. And given that we are dealing with expansion of a market to which many small 5 to 10 electrolyzer solution had been implemented, this one is the first of a bigger scale. And of course, we see announcement for many larger projects being developed. But the lesson learned here is very important. And just to show you the plant itself, it looks very scalable. You have 4 5 megawatt electrolyzers with 4 rectifier just next to it, all within one building. So very easy implementation within a building. And to do a bigger building, you just need to line up more rectifier with hydrogen And you see, aside from the building and the electrolyzers, you have next to the building the cooling systems, which is important to keep the heat that is being generated during the production of hydrogen, to ensure that everything stay cool. So you always need outside the building cooling systems. So this shows a plant with 20 megawatt. One of the cell stack within the building. This is how it's looking like. It's very neat. Each 5 megawatt electrolyzers are included in a glass box, which keeps the hydrogen within a closed environment to make sure the rest of the building is less exposed to any emissions of hydrogen in case there are any leaks. So this is a very safe environment. Hatch delivered this project with Air Liquide late in 2020. It's in operation and functioning very, very well. Now, when you look at the scale up, you can look at Cummins, which I just showed in the scale up form, or you could look at how it could be done to other vendors. Here is an example with ThyssenKrupp 120 megawatt PEM electrolyzer, which is simply assembling hundreds of small electrolyzers stacked next to each other in a big building. The stacks are all associated with rectifiers on the upper left of the screen, all within one large building. So in this way, you can scale up a electrolyzer from few hundred of megawatt to thousands of megawatts by having several buildings. This is where the market is, and big players like ThyssenKrupp, Nel Hydrogen, Siemens, and Cummins are examples of companies that can deliver large-scale hydrogen projects. Now, if I go to some applications of green fuel from green hydrogen, I'd like to show pictures from ThyssenKrupp, where combining a hydrogen facility here on the bottom part of the picture with an industrial client that would be emitting CO2 emissions. By capturing those CO2 emissions and using the hydrogen produced using wind, solar power, for instance, or even hydropower, you can combine the CO2 with the H2 to produce methanol. So you see the methanol plant. From the methanol plant, you can use the methanol to combine with the gasoline to be a green fuel. That's a very nice applications of using green hydrogen, doing carbon capture to develop a fuel that is based on green energy, and also capturing CO2 emissions from another plant. Another types of applications would be less obvious here, but this is a green ammonia plant, so much simpler than an ammonia typical plant, which is using natural gas and steam methane reforming to make the hydrogen. In this case, you have on the right a building with a stack electrolyzer in orange within a building, and the hydrogen being produced goes to the left, where you see those big columns, which are the ammonia processing plants that combines nitrogen with hydrogen to make ammonia. Now, the nitrogen is simply an air separation unit device that uses electricity, and it can use green electricity to extract the nitrogen from the air. The hydrogen is obtained from the electrolysis and combining to the processing ammonia plant, combining H2 and N2 together gives the ammonia, the NH3 molecule. So green ammonia plant, it's much simpler than a steam methane reforming ammonia plant that we see typically everywhere in the world. So those are becoming very popular to produce ammonia from green hydrogen. Now, just to give you a sense of the footprint and the pricing of green fuel. So if you look at natural gas, just to give an example, I mean, in different regions of the world, natural gas is definitely of a different prices. But let's say I give an example of $5 per gigajoule or a million ton BTU if you prefer. And in the future, 8 years from now, if we assume a carbon tax, which in some jurisdiction is increasing and some doesn't, that is going to be seen. But in Canada already by 2030, carbon tax should be up to $170. So that has a different direct impact on the price of natural gas. Natural gas plus the carbon tax would triple the price of natural gas in 8 years. May not happen, but just as a scenario, that's what it would look like. In terms of the hydrogen, if I look at the price producing gray hydrogen today, it's about $12 per gigajoule. For those that are more familiar with the price per kilogram, it would be $1.5 US per kilogram. And the green hydrogen can be produced at $36 per gigajoule, or about $4.5 per kilogram. And it is expected that within the next 8 years, production of green hydrogen should shrink by at least 50%. And so we would go from $36 per gigajoule to $18 a gigajoule. So we're looking at between $1 to $2 per kilogram for hydrogen production by 2030. And you see that at these prices, hydrogen, which already competes with diesel and gasoline, will be of the same order of magnitude as the price of natural gas by 2030. So that's very important because a lot of big application using hydrogen are made using natural gas. So if we can produce green hydrogen with green electricity at a price that is competitive with natural gas, many different applications could be greened using hydrogen as opposed to natural gas. In terms of methanol and ammonia, currently on the market, methanol is about $20 a gigajoule. It's pretty much the price of diesel and gasoline before all the increases we have seen in the last 3 months. For green methanol, we're looking at $30 per gigajoule. So it's about 50% more expensive today to produce green methanol as opposed to the conventional methanol. But in 2030, green methanol would be cheaper than the regular methanol for the reasons that producing hydrogen from green power would be much cheaper back in 8 years from now, and also methanol from fossil fuel would be taxed and it would cost even more money. Similarly, for ammonia, it's about 50% more expensive to produce green ammonia right now. But in the future, it's expected to go down to about $800. So ammonia, green hydrogen, green methanol will all compete with fossil fuel equivalent by 2030. So that is very exciting. It gives us a pathway to decarbonize and bring the energy to fossil free fuel. For the hydrogen fuel cells on trucks, there's a big truck that has been shipped to South Africa. This is the kind of truck, 300-ton diesel truck that has been converted to hydrogen with 800 kilowatt of fuel cells, and it's going to be operating using solar power to make hydrogen using a 3 megawatt electrolyzer. On the truck, you have hydrogen storage, and so the truck will be fully electric with batteries, fuel cell, and hydrogen storage, and it should be fully operational this year. This project is done by Anglo American. We did help on optimizing the sizing of the hydrogen storage and the targeted pressure for the tanks. So that's beautiful applications of hydrogen. And finally, just a few words on renewables and hydrogen. For off-grid, we have implemented this project at in a mine in northern Quebec, 6 megawatt of power, 3 megawatt of battery on a microgrid. The mine, a nickel mine, has a 20 megawatt load, and of this load, 6 megawatt of wind power is used. And to keep the grid stable, we have a battery, we have a Hatch microgrid controller, and any wind excess is stored in the form of hydrogen using an electrolyzer. And whenever the wind power is smaller, the hydrogen stored is sent to the fuel cell to produce electricity. The project so far has displaced more than 50 million liters of diesel. The project is owned by Tuglik Energy, and Hatch supported the development of this project in multi-phase since 2014. In 2018, we added a second wind turbine, and we're planning for more in the future. And this is how it looks in terms of the battery, the electrolyzer, and the fuel cell. Those are smaller scales. With the hydrogen tanks, 300 kilogram of tanks of hydrogen. And so this is in the Arctic. So as you can see, the background is beautiful, but very icy and cold. But this is an example of combining flywheel batteries, hydrogen systems, and wind power on a microgrid to offset carbon emissions from diesel using wind power and using storage and batteries to control the wind power variation to keep the grid stable. Another example I'd like to share, that would be the last one, is how on large scale grid, if we combine wind and solar to make hydrogen, we use hydrogen storage in the form of salt cavern, and the hydrogen produced is used to gas turbine. So here's an example in green of a combining wind and solar together. You see the profile. The green is the production of wind and solar combined. It does vary quite a bit from day to day, but in average, you can see that throughout the year, the production is fairly constant, a little bit less in January and December, but aside from that, it's pretty constant. The dark blue line is the 300 megawatt electrolyzer, and the lighter blue, it's a 180 megawatt electrolyzer. This is the target production we want in average for the hydrogen, so we need to firm the hydrogen production to be constant for the gas turbine. And as a result, we want to integrate as much renewable power as we can. And as you can see, often the hydrogen production, the renewable production is higher than what the electrolyzer can absorb. And so that's the kind of pattern that we see, where the target is 180 megawatt production. So when we produce more, up to 300 megawatt, in orange, the hydrogen produced is being stored in a salt cavern. And in the blue section, the hydrogen produced is directly used to the gas turbine. And in the gray section, the electrolyzer is not able to produce sufficient energy, so the stored hydrogen is used to ensure that we have enough hydrogen to meet the blue bar. So you can produce hydrogen in a constant fashion by producing more hydrogen when the renewable power are present, and store the excess in storage. And when there's less renewables, then you can use the stored hydrogen to maintain the hydrogen production for the gas plant. In terms of storage, here we have 800 tons of hydrogen in a salt cavern. And here's this curve shows how much hydrogen is stored in the salt cavern. And as you can see, from the beginning and the end of the year, the storage started at 350 ton and it ends at 350 tons, but it increased during the year and then reduced during the year. Salt cavern allows to store hydrogen in a seasonal fashions. And the storage is minimized because we're combining wind and solar. If we had solar only, and that's almost my last slide, if it were only solar, you see the distribution of solar. During the winter months, there's a lot less summer, particularly in northern Canada. And so there's a bigger gap to absorb during those months. And if you want constant hydrogen production, then it means you need to store more. And storage with solar production only would take 4,000 ton instead of 800 ton. And that's the pattern you would get from the salt cavern storage with a lot the storage being depleted during the winter months because of low solar production, and the storage maxing out during summer months where the solar production is maximized. So the key point here is by combining wind and solar, it allows to produce a constant amount of hydrogen with a lot less storage because we combine the two resources together. And on that, that's all I wanted to talk about. Those are fantastic applications that can be implemented across the world. So if you have any question, my pleasure to answer.
Thank you very much, sir, for this informative presentation. And if anyone has a question, please, you are welcome to ask me.
Hello, Dr. Michel. I have a question, please.
Yes, go ahead.
Actually, I have an experience in the field of electrical energy and so on, and I have this how to connect two or more than one source of electricity. For instance, a gas and a diesel generator, also wind turbine and so on, and how to synchronize between them and so on. And I wonder if you can recommend me a book or something to read about how to synchronize this new technology. I mean, how to synchronize two or more than one source of P2H, for instance, or something like that, how to be sensed electrically and so on.
Yes. So, well, first of all, each generation assets has its own controller in terms of responding to grid frequency and ensuring that it contributes to maintaining the grid at a given frequency. But then you need a microgrid controller that coordinates those assets in terms of what dispatch power they should provide. And if you have renewable, which are less controllable, you need energy storage. So the microgrid controller talks to the battery. The battery will inject power or charge or discharge as a function of the wind or solar power fluctuations. Will coordinate with the generators, the gensets, gas turbines, to ensure that the sum of the power meets exactly the load but to maintain grid frequency, you need fast generation assets like batteries, which will inject power or take power away from the grid to maintain frequency and voltage. So the microgrid controller's job is really to control the battery and curtail the wind and solar if there's really too much renewable powers. And in coordination with the gensets, particularly if you have sufficient wind and solar with batteries, you may be able at some points to shut down the reciprocating engine or the gas turbines and have the battery do the grid forming and maintaining frequency only on the battery. That's the role of a microgrid controller. So Hatch has one, Siemens, ABB are big players in the field that have these kind of technologies to integrate multiple sources of energy production to maintain a microgrid stable. So do you have any more questions? I think I see one says, what is the most, the most
Mr.
economical? Yes, go ahead.
He is asking what is the most economical and profitable mode for the production of green hydrogen, solar or wind?
Well, so the cost of hydrogen production is directly related to the price of energy. So wind power today in many jurisdictions in windy areas is much cheaper than solar. But on other regions, solar prices are getting very small as well, particularly in Northern Europe, Africa, and in India, and also southern US, like Texas. So you combine those energies to produce green hydrogen. The challenge is not so much just the cost of the wind and solar. The challenge is you have to deal with the variability of the wind and solar, which will produce a lot more than what the electrolyzer can do. So you need to optimize the size of the electrolyzer, not too much, such the project doesn't touch too much. If you size the electrolyzer about 30% more and your wind and solar is about 3 times, you put 300 megawatt of wind solar together with an electrolyzer of 100 megawatt, you'll lose most of your renewables and your capacity factor for the electrolyzer may be down to 50%. And so your cost of hydrogen is going to be more expensive. So the best is to be able to have combined hydrogen production with a fixed load of renewables from hydropower or maybe even grid connected that has a little bit of fossil fuel, and have 50% of the energy met by renewables. In this way, you can have an electrolyzer that has more 85% capacity factor. Your cost of hydrogen production is going to be cheaper. And that's the key here. It's just renewable with hydrogen would lead to more expensive hydrogen production because of the wind and solar excess that the electrolyzer cannot absorb.
Thank you, sir. There is someone who is asking if you can send the slides of her presentation.
Yeah, I'll send it to you. Yeah.
Okay, thank you.
Okay, any more questions? Last call. Okay, thank you very much.
Thank you. I think there is no more question. Thank you very much, sir, for your lightning presentation and for answering the question for the attendees. I hope we will see you in our future events.
Okay, thank you, Manuel.
Thank you. Thank you
Bye-bye.
so much. Now, guys, we will move to our second speaker. I will give the word for my colleague Ala to first introduce her.
We have a guest speaker, Dr. Ashraf Radaideh, Chairman of Electric. Hello.
We hear you, Ala.
Yes, we hear you.
Dr. Ashraf Radaideh, Chairman of Electrical Power Engineering Department, Hadjawi Faculty for Engineering Technology of Yarmouk University. He will talk about smart grid recent operational challenges. تفضل دكتور.
Hello, everyone. Do you hear me, guys?
Yes.
Okay. What about the video? So actually, I do have some internet problems here. So when I turn on my camera, actually tells me that there is some kind of internet problems. But we will see. I will proceed first, and then if I face any problem, then I will disconnect my camera. So hello, everyone. First of all, I would like to thank you all for being here in this wonderful gathering and wonderful preparation from young professionals such you guys. To be eager to hear about the advancements of the power system, which is really a very good also opportunity for me to talk about the smart grid advancements in the power system. So as Ala, thank you for this nice introduction. I will also introduce myself again. My name is Ashraf Radaideh. I am the department head of Electrical Power Engineering at Yarmouk University. And in today's presentation, I will be mainly focusing about the global trends in the electrical energy sector, the renewable energy sources in power system, what is the emerging operational challenge, probably in the previous presentation you have heard about the hydrogen and some kind of energy storage technology and the new challenges in the power system. I will give more emphasis in this presentation, but the orientation will be toward the smart. Then I will talk about the modern power system in general, what's the meaning of smart consumers and how to be a smart consumers. We'll then talk about some demand response programs, what so-called the time of use electricity pricing and the direct load control. Then I will talk a little about net metering and finally the Phasor measurement units. So what are the global trends? So as we all aware that the worldwide policymakers have made a clear roadmap and targets to replace all of the conventional power plant, which is mainly based on fossil fuel, and replace it with renewable energy. And why is that? Because we do have a limited fossil fuel supplies. We do have the greenhouse emission and the global warming, and also the fossil fuel costs, it costs a lot of money, and also their prices are not fixed. It keeps changing all over the time. So this kind of disadvantage regarding fossil fuel and mainly the greenhouse emission and the global warming have made the policymaker to establish a clear roadmap to replace or to increase the penetration level of renewable energy. When we say a penetration level, it means that the percentage of renewable energy that produce or participate in producing electrical energy to feed the load. This what called is the penetration level. Why we do that? Because renewable energy is considered as a secure source of power. We do have a clean source of energy and environmental friendly. There is no any kind of greenhouse emission or CO2 emission involved in production. And also in renewable energy, it's economical cheap source of power. There is no any, we don't pay money to receive the sun radiance, or to, we don't pay money for wind. So for operation, from operational point of view, it costs nothing compared with the conventional power plant units. So in general, this kind of an overview of all renewable energy sources exist in the power system. We do have wind, solar, the hydropower, we do have the biomass, and we do have extraction of the energy content exists in tides and also in waves. And actually, just before the presentation, I discovered that I have missed the geothermal, which is the one of the credible and important renewable energy sources which exist nowadays. But renewable energy, actually, they differ from the existence or the availability. Some countries, they do have dams, they can install or they can extract the energy in the dam or in the hydro turbine. Some countries, they do not actually, or they do not have access to tidal energy or the wave energy. The most available sources of renewable energy are the wind and solar, and I will be focusing on the wind and solar today to open what's the new challenges that we are facing. As we can see in this figure on the left, this represents the output power of a wind farm for 30 days. And also for a complete 24-hour. Excuse me. So as we can see here, the output power of the wind farm is actually different from one day to another. Just one moment, guys. So sorry again, guys. So I was talking about the wind farm output, which is mainly variable, and probably you know from the previous presentation, they mainly talk about the storage, and the main advantage of storage elements is to come up with what's called the variability and uncertainty. So this is a typical output of a wind farm. So we can see that the output power from day to another is different than, each day profile is unique from the other. This is one point. The second point is the output is variable. It's different from 1 hour to another, and sometimes it's different from 1 minute to minute. So there is one main thing here, that this recorded data for a complete 1 month. But if we want to expect the output power for the next month, then we have to use advanced algorithms such as the neural network to make kind of prediction. So in power system planning is a major point or a major thing that we have to think about. And the main tool of the planning is the prediction. When it's come to renewable, the prediction it's coming with a very narrow band. It's called uncertainty. Then we have to deal with the prediction errors. So the output power will not be fixed. It will be kind of variable and also uncertain when we talk about prediction. The same thing applied for the solar. Yes, we know the pattern of the solar output. We know it's like producing the peak hour during noon, and it's producing less during the morning hours, less during the evening hour. But we know actually the pattern, but the exact value we don't know unless we operate in real time. Then we know exactly how much the output power. Also, in case of the cloudy days and rainy days, the output is variable. Same challenge as the wind output power. So what also an additional challenge regarding the solar energy is what's so called the net load. The net load is defined as the actual load exists in the network minus the output power from renewable. So in countries which are dependent on the solar energy, when they see the sudden drop in the solar panel, the net load will be a kind of sudden increase in the net load. So this increase can be seen in regions that dependent on the solar panels, such as California. So this increase, this very high ramping requirements should be compensated by a fast-acting units or fast-acting peaking units. And these units actually may not be available at all in the network. So there will be a challenge, or there will be a challenging problem to the operator to cope with this kind of sudden drop. So we need to compensate for this. And as I have said, the compensation can be done using the fast-acting peaking units or by using storage elements, as we will discuss in this slide. So we have seen in the previous slide that the output power is not fully controllable, variable, and uncertain. Example was from the wind and solar. And also, if we will increase the penetration level, this will leave the system with low inertia level. This is an important point. What we mean by lowering the inertia. So before the renewable energy penetration, or before introducing the renewable energy to power system, we used to rely on the conventional power plant, which is based on nuclear, gas, natural gas, or any other kind of fossil fuel. So these are based on, previously it was the main source of the system inertia. It was really mechanically coupled. So, and also we know from the operational point of view, our objective is to increase the size of the power system. Mainly our objective is to increase the size so that the system will become more robust. The system will be rigid to face all kind of disturbances. Nowadays, as we replace the conventional power plant with renewable energy, which is has less, or because of the DC coupling, they don't have any kind of inertia. This will highly affect the stability of the system. So the system will become weaker and weaker, and even a small disturbance or a small fault may cause even serious, may cause brownout or cascaded failure to even a blackout. So there is a kind of a payoff or payback if we want to increase the penetration level from the stability point of view. So for such challenges, we need to improve the grid resiliency to address these emergencies. Grid resiliency means flexibility. So our grid, to increase the penetration level, we need more resilient grid. We need it to be more flexible. So what are the solutions? We need a grid scale, cost-effective storage element. Cost-effective is a big word here, because there are like many research and development is going on in order to find a kind of cost-effective storage element suitable to be operated at the grid scale to store energy and release the energy when it's needed. On the other way, we may invest on demand flexibility, as we will talk in this presentation. And it is actually one of the objectives with smart grids is to increase demand flexibility, to make the demand is flexible. So demand is traditionally known like the profile is given, and we need to commit, and we need to commit the generation to cope or to deal with the load. But we can think to demand in different ways. So how we can increase the flexibility, or can we increase the flexibility with the demand? And this is, as we said, this is the target of the smart grid. So we can reduce peak demand using demand flexibility. We can increase the energy efficiency awareness, which means reducing the energy consumption, overall energy consumption. We can actually do load shifting and load controllability. All of these things will be addressed in the coming slides. And we can also coordinate between the end users and utilities for optimal operation. And this is something a must with these kind of operational challenges. So I will not spend too much time on this slide, but actually it's an overview for the storage facilities that exist in the power system. Some of them, they do have energy conversion. They convert electricity to another form, or some of them, they do not. Like the supercapacitors, or of course, the supercapacitor, the supercapacitor may exist in a high power profile, or could be in the high energy profile. And also the superconducting magnetic energy material. So in such storage facilities, we do not have an energy conversion, because these are electrical devices. However, they cannot actually be they can be used, but as we can see from in the megawatt time scale, but actually they are available only 2 seconds, which means that the energy content, the energy stored in such technologies are very small, and they can provide only power with very short time. Actually these kind of storage technologies, they are suitable for the high cycling application, as we probably they can be used to smooth the variability in the wind farm, for example. But as I said, because it does not have energy conversion, the energy content or the energy storage content is somehow small. And also we do have the batteries, all kind of batteries, lithium ion and nickel or lead acid batteries. So there is a lot of research and development is going on to increase the capability of the batteries, such that we do have, for example, batteries exist in the megawatt scale and also can last energy for hours time scale. Then as we can see, because energy is the production of instantaneous power, and time like the energy content in such technology will be improved with the time and with the research and the development. Other technologies that involved energy conversion, like, for example, the compressed air or the pumped hydro storage, where we store energy in an elevated water and restore this energy by using a water turbine, or the compressed air by stressing the air inside tanks and use the pressure turbines. Or we can stress it not in tanks, actually in underground, in the underground. we can use the underground as a tanks, then release this stored air to a pressure turbine and produce electricity. This kind of, and also we can cool and pressurize the air to liquefy it and then store it in tanks and then use the exchanger and turbine to produce electricity. So as we see in these examples, there is a kind of energy conversion, or also the hydrogen cells, or all the kind of fuel cells to use the excess energy from renewable to produce hydrogen and then reuse the hydrogen back to produce electricity using a fuel cell. So this kind of technology where is energy conversion involved, they can be scaled up. They can be in a megawatt or a gigawatt scale, and they can produce a lot of energy and can last for hours. And actually, this is the main thing that we needed to increase or to allow increasing the penetration level from renewable. We do need such a grid scale storage facility to be exist first. So traditionally, as a comparison between the traditional grids and the modern grids, traditionally we do have the thermal or the fossil fuel-based conventional power plant, and we use the grid to transmit this power using the substation and then back to the consumers, the main consumers, industrial and commercial and residential buildings. In normal operating conditions, actually the operator will do nothing or will do minor things, because the only dynamics that involved in the grid is that the load is changing. So we need normal operating condition. He will do a unit commitment. We will do a economic dispatch, optimal power flow contingency analysis, something. They will, like, as I said, there will be no lot dynamics involved. In emergency conditions, the operator will only isolate the faults and so on to prevent cascaded failures. So what the things that switch the operation of the system is that we have now many new things that we have to deal with. Now we do have, of course, we will have the conventional power plant, which is thermal, nuclear, and also we do have the customers, industrial, residential, and commercial, but we also do have renewable energy. We do have the storage elements, and we do have microgrids and the electric vehicles. So, so this is the new picture of the system, that what we call it a modern power system, or the smart grid. So what makes this a grid smart is the optimal coordination between the various entities that we have seen in the previous slide and the end users. Why we do need this optimal coordination? To maintain grid reliability, security, and stability. These main three objectives: reliability, increase the reliability, security, and also stability, while minimizing the operational costs and environmental impacts. So we do need to minimize the operational costs and environmental impacts. This is how we can achieve this objective, by increasing the renewable energy penetration level. And how to achieve this kind of coordination is the modern technologies that allow two-way communication channels and also facilitate the automation to respond smartly to the system dynamics. And this is the main objective of smart grid, is to automate, actually, to automate the response to the different things in a more systematic way. So the main, the first thing we will talk is we need to invest on demand flexibility. And one objective of the smart grid is to make the consumers smart. So in order to make it smart, we need to talk with the consumers. We have to give him some information, take from him some information. There is an important tool that exists at each site of the smart consumers. It's called the advanced metering infrastructure. The traditional meter only record the power consumption and the energy consumption. It's give some of the new digital meters will give you some voltage on or current readings. The advanced metering infrastructure, or AMI, it allows two-way communication channels between utilities and end users. So there will be an information exchange. The utilities can send, for example, the price of electricity. They will send a price signal, or they can receive the power and energy consumption. They can receive the energy and power consumption at the end user sites. And also the end user can receive from the electrical utilities a different orders, for example, charge the vehicle or do something. And this is the rule of the AMI, is to make sure that we do have two-way communication channels between the utilities and the end user. On the other hand, these information provided from utilities can go to something called home energy management system. And this is a software installed in locally inside the home, and can do different objectives. For example, the home EMS, or energy management system, can track daily and monthly energy consumption to allow energy efficiency. Energy efficiency, as we said before, is the objective to reduce the energy consumption, reduce the load profile. So this will not happen without increasing the awareness of how much I have consumed so far, or how much the bill, or how much my electricity bill will be. So this is the main objective. This is one of the objectives, the home EMS, and also to automatically use power when price is low, can choose setting that allows specific appliances to turn off in case of emergencies. So this home EMS also can take the price signal coming from the electrical utilities, do some kind of optimization algorithm, and see where it's optimal to, for example, do washing, or cool the pump, or do any kind of any functionality which depends on electricity, or it can turn off or dim the light to reduce the electricity bill. So this is the objective home EMS, and also one of the objective, or one of the requirements for the home EMS, that it should interact with the different appliances. It should interact with the air conditioners, with the smart thermostat, as we see, the switches, the washing machine, with the electrical vehicles, with the rooftop. So it have to interact with the different components exist in the system and see what's the optimal operation that should happen in order to save bills or to save money. So one of the examples of the price signal that the end user can receive, as we say, using the AMI, something called the time of use electricity pricing. What's the idea behind the time of use? We know that electrical utilities, in order to meet the load actually, it has a shape like this. Typically, it has a shape like this. So any load, it has a peak value, and this peak value, in order to feed or to make sure that the total power generation is equal to total power demand, we need, in order to feed this kind of, for small period, we need to turn on something called peaking unit. And what this peaking unit, it's only turn on, it has a very high ramping capability, as we said before, and it costs a lot of money, and this cost actually will be reflected on the price. So one of the main challenge or one of the main price management from the operational point of view is to prevent operating such fast-acting or peaking units, because they will cost a lot of money and their price will be reflected on the price of electricity. So the time of use philosophy, it's only or it reflects the cost of generation of electricity. It will be reflected to the end user. So the end user will pay different price based on the time he uses electricity. For example, in this time period, he will pay a lot of money. But in this called peak period, and this period called off-peak period. So during the off-peak period, he will pay less. During peak period, he will pay more. So what the home EMS will do to take advantage of such price signal is to do load shifting. So instead of using electricity at this time, instead of use dishing machine or washing machine at this time, we can postpone the washing machine to the early morning or the afternoon hour. So we can take advantage of the low price period and avoid using electricity using the high price period. And this kind of load shifting is very useful from the operational point of view, because we will reduce the peak. It's called peak clipping, reduce the amount of peak. And we will do also load shifting. We will move load demand from peak hours to off-peak hours, and finally we have a valley filling. This kind of valley will be filled with load, and we will end up, if we have a full demand flexibility, we will end up with a flat load profile. And this is a very desired from the operational point of view, because it will not, for example, commit peaking units. It will rely on the base units, for example, like coal and nuclear, and we will not be forced to use any peaking unit, as we said before. So this is what I have told you, or in this slide, called demand response, because the demand or the end user have response in a different way, other than what is expected or other than what he usually do. We have also another form of demand responses called direct load control. Direct load control. And this, utilities can motivate the end users. It's need motivation, so the utilities can pay the customers through incentives to give access to less priority loads. So the electrical utilities through the AMI and home energy management system can access the internal load in houses. So they can remotely, for example, turn on or off some devices according to the grid needs. For instance, the end user may give access to their cooling and heating system to adjust the temperature set point or modify the energy consumption accordingly. So the end user can make classification, can classify the internal loads inside the home. Some of them are critical, so they are not allowed to be controlled from the electrical utilities. Or some of them, for example, unwanted lighting, or for example, ±2 Celsius from the air conditioner or ±2 Celsius from the water heater, can be given as a privilege to utilities to be controlled. So electrical utilities can control these kind of loads remotely. And yes, from the end user point of view, it's not that much not that much effect. But when we talk about the aggregate level, when we talk about millions of devices, then at the aggregate level with the proper coordination, this can be used, the direct load control, to minimize the effect of renewable variability. As we have seen before, the wind output power is variable. So we can smooth it out using the direct load control. Or the uncertainty. The uncertainty is revealed only when we operate in real time. But when we talk about prediction, always we do have this kind of uncertainty in renewable energy output. So we can utilize this kind of demand response programs, the direct load control, in order to smooth it out. It also can be seen as a massive grid scale storage system. For instance, if we have houses with good thermal insulation, we can store thermal energy as, for example, pre-cool the houses before the peak hours, for instance. Or, for example, preheat the water inside the water heater. So we can giving some temporary storage to the grid. And again, at the aggregate level, it can be seen as a grid scale storage system. It also can replace load shedding schemes. Power system operator, in order to save the system in case of, for example, a power plant went down, or there's some kind of disturbance at a power plant, and it turned off. So in order to save the frequency and prevent cascaded failure, operators what actually do, actually the last choice is to do load shedding, is to shed the power from load in order to make the balance again, to retrieve the balance again, the balance between the generation and the demand. So this kind of schemes, that like load shedding schemes, you will turn off light, you will turn off the power, shed the power to a complete city, regardless of being some critical load or not non-critical loads. But this kind of programs can give a replacement or a plan B to be conducted. Instead of using load shedding, we can only shed the load from the uncritical loads. Or it can also replace spinning reserve, because the demand is also synchronized to the grid, that can be considered can replace the spinning reserve. Electricity price management, as we have seen in the previous or the previous slide, we can reduce the peak. If we can reduce the peak, then we will no longer be forced to commit the peaking units, which are very expensive. Then we can use it as electricity price management, this kind of demand response program, and then reduce the peak hours or the peak demand. We will no longer be forced to commit expensive units, and the price will be flat somehow. Okay, net metering, it's also one of the facets of the smart grids. What's the meaning of net metering? Is the power flow, is measuring the power flow in both directions, to the house or to the grid. So it's given an opportunity for the end user to actually sell electricity to the utilities. So, and also variable price rates also applies. So what's the advantage of net metering? Why we do need to measure the power flow in both directions? It's actually encourage the end user to use the distributed renewable energy sources like the rooftop. So I can use my rooftop, or for example, to sell electricity to the electrical utilities during the peak hours, because the price for electricity is high. They will pay me a lot of money. And I can again, for example, install and battery storage inside my house. I can store electricity from the off-peak hours when the price is low, and then resell the electricity back during peak hours. So this kind, and also encourage the support the objectives of achieving a microgrid in the distributed in the distributions, and also give utilities access to the distributed storage elements. As I said before, we do have batteries, and we may have also the electrical vehicles. Using the advanced metering infrastructure, for example, the electrical utilities can get access to the inside battery, and if the utility in need and the customers have paid good incentive, they can give permission for their batteries to be controlled, the distributed batteries. Or, for example, they can give access to the electrical vehicle if there is an extreme emergency situation. We may extract power from the electric cars and get the energy stored in the electric cars and use it to the grid to save the grid from, for example, a cascade failure or a blackout. So this is one of the advantages of the net metering, is provoke the using distributed generation like the rooftop, and also can give access to the electrical utilities for different resources at the distribution site. The last topic is what's so-called the Phasor measurement unit. So what's the Phasor measurement unit? Actually, I think I have expanded the time. I have used more time, right? We used to finish in 30 minutes. I will wrap up. I will wrap up only in short, because this is one of the important topic that exists in nowadays, is the what's so-called PMU. So PMU is a Phasor measurement units. This is an acronym of what's so-called Phasor measurement units. Previously, in the traditional grid, not smart grid, traditional grid, they have used SCADA system, which measure the voltages, currents, and different measurements from different sites at a cycle of 2 or 4 seconds. And this kind of time frame is considered very huge if we are talking about disturbances, or when we talk about variability in wind, for example, which can, for example, there is a cloud and there is a sudden drop in the solar generation. So in order to capture this kind of very fast acting dynamics, we need a new technology, different or better than the old one, than the measurement from CTs and VTs of this SCADA system. So we do need what's so-called a PMU device. What's a PMU, Phasor measurement unit? It's a device that produces synchronized phasor estimates. So it can produce magnitude, angle, and frequency at a very high sampling rate, 30 samples per second. It can give a 30 samples per second. And what also good about PMU is a synchronized measurement. So these measurements are synchronized by a GPS signal. So we can use it for real-time monitoring and control, for event detection, identification, and qualification. We can use it for real-time congestion management, and for what so-called self-healing, because we cannot, in order to make an automated grid, we cannot actually base control action on something that it's not reliable. So we need something that represents the system now, and what's actually is done by the PMU. robust power system restoration after blackouts, because synchronization is a big deal and we need fast measurements, and also enables monitoring microgrids and islanding, and finally, dynamic model validation. And this is actually an overview, a big picture to the smart grid, because smart grid is not something can be given in 30 minutes. It's need actually a full course to be covered in details. But as we have seen, smart grid is the modern view of the traditional power system, and also it guarantees an optimal performance interaction between the conventional power plant, renewable, and the end user and the storage. And also it can be seen as a fast-acting communication channels. We need this kind of communication between the end users and storage and all the entities in order to optimize, in order to use this kind of optimization algorithm and automated control action, so such that the operation of the grid will be economically and environmental friendly and improve the reliability, security, and stability. Finally, demand flexibility, as we have said, and grid scale storage are the major components of smart grid, and they have to be utilized in order to improve the penetration level in the future. This all from my end, and if you guys have any question, I will be more than happy to answer. Do you guys have questions? Okay, if there is no any questions, something in the chat, I think. Okay, if there is no question, this is all what I want to talk about, and it was really my pleasure to talk to you guys, and keep it up. And
thank you, Doctor, for joining us. Thank you.
Thank you so much.
Thank you.
Thank you so much, Dr. Ashraf and Dr. Michael, for sharing your experience with us today. It was extremely helpful and interesting, and it's really wonderful to see you here today with us. Now we would like to extend a special welcome to our special guest speakers, Mr. Aymen Tmar. Mr. Aymen is the IEEE PES Young Professional Region 8 representative and the chair of the IEEE Tunisia chapter for 2021-2022. And he was the chair of the IEEE Tunisia Young Professional Affinity Group for 2019-2020. Today, Mr. Aymen Tmar will speak to us about how to grow your career with IEEE PES Young Professional. So welcome everyone. I hope this webinar inspires you idea and decisions. Let's start. I'm gonna leave the word for you, Mr. Aymen.
Thank you, Nadem. Hello, everyone. Do you see my screen?
Yes.
Good.
Yes.
Welcome everyone to our session. This is with the title of Grow Your Career with the IEEE PES Young Professionals. My name is Aymen Tmar. I am an Asset Integrity Engineer at Amilcar Petroleum Operation, and I was working for Shell Tunisia Upstream for 4 years. I started as a member for IEEE since 2015. I served IEEE in several positions. Since I was a student, I was the Power and Energy Society chair of any student branch and the chair of Industrial Application Society, as well as the vice chair of INISSB, a student branch. Then after my graduation, I have continued volunteering with IEEE. I was the chair of IEEE Young Professional Tunisia section for 2020, from 2019 to 2020. And I'm now the chair of Industrial Application Society Tunisia chapter for 2021-2022. And in the same time, I'm the IEEE Power and Energy Society Europe, Middle East, and Africa Young Professional Representative for Region 8. I would like to thank you for having me today in this gathering. It is my pleasure to be today with you, and I'm really happy to see this kind of event and partnership between different countries in MENA region. I hope this will continue in the future, and I would like to thank you all for the great organization. Really very well done. Let me start by introducing IEEE PES Young Professional. The IEEE PES Young Professional is the group of IEEE members and volunteers who have graduated from their first professional degree within the past 15 years. It is an international community whose members are interested in evaluating their professional image, expanding their global network, connecting with peer locally, and giving back to their community. It's very, very important to give back to your community after your graduation and gain knowledge and experience, work experience. Since it's encompasses all members from recent university graduates to experienced professionals and entrepreneurs. The group is highly diverse in what it has to offer. And currently now we have more than 8,000 IEEE PES Young professional members. So as you see here, this is our website, psyp.org. I'm inviting you to visit our website and see our updates. So this is our committee for 2022. The executive committee led by Simai Akar, as you see, and we have PS liaisons for Women in Power, humanitarian activities, student chapter activities, and PS Day. And we have as well a student subcommittee coordinator for marketing and communication, professional and educational activities, new initiatives and projects, membership development activities, initiatives, outreach, entrepreneurship, event and conferences, and the technical activity coordinator. And we have a regional representative. We have divided the world into 4 regions, one for United States and Canada, myself for Europe, Middle East, and Africa, Harun for Asia Pacific, and Luis for Latin America. And we have webmasters and global YP Summit coordinator. Okay, in the region 8, we have as well a sub-regional representative, one for Europe, one for Middle East sub-region, and one for Africa. And we have we are aiming to have PSYP representative in every country in our region. So I really encourage you to apply for this form and join our team. You are more than welcome, and I'm sure that you have a potential and added value to our community and PS in general. So this is the link, and if you can make screenshot and then apply in this call. By joining our team, you will be working with different subcommittees, as we have discussed previously in committee slide. So we have technical activities, professional activities, and many more, and liaisons for women in engineering, in power, and students. Our objective as Region 8 PES representative is to engage PES Region 8 young professional members in large-scale technical events and address their needs to access to recent technical content, ensure the success of IEEE PES young professional events, projects, and initiatives in the Region 8, improve young volunteers' sense of belonging to IEEE PES and the sense of recognition, improve activity reporting and increase visibility of IEEE PES Region 8 young professional events and programs, track behaviors on which to develop programs to address the need and wants of members, identify successful volunteers and enable them to advance their volunteering career in IEEE PES. This is some of our past event for 2021. We participated on the IEEE Power Africa conference, young professional panel. 3 of our committee was present in this panel session, Simai, myself, and Adedoyin. We have discussed many topics related to young professional opportunity for involvement in the power and energy sectors. How can we contribute to the energy transition and afford more and cleaner energy? We have participated in many sub-regional SYP student and young professional congress like Africa SYP on December 2021 with Ghana with the title of how IEEE PES young professional can help you grow your career. We participated as well with technical presentation with the title Advanced Corrosion Monitoring System for Risk-Based Management of Pressure Vessel and Pipeline on the Central European Student Young Professional Congress, as well Middle East Student Young Professional and North Africa SYP. Our big event for 2021 is the Powering the Future Summit. This summit is focusing on providing most up-to-date professional and technical training to the members at the early stage of their career. The summit was hosted online on 23rd, 24th, 13th, and 31st of October. The mission of this event was to empowering the power and energy leaders of tomorrow. The summit provides a premium platform for engineers, students to share their knowledge and ideas with the professionals from around the world. It aimed to upskill professionals, headlight on advancement in technology and entrepreneurship, and highlight success stories. The summit was in form of tutorials, plenary sessions, technical talks, and virtual industrial visits with distinguished speakers delivering speeches on emerging technology in the power and energy sectors. Attendees has the opportunity to gain in-depth knowledge of the same. In addition to improving their technical ability, attendees has the opportunity to learn from and interact with industry leaders from across the world. There is other pre-event was held like networking beyond the board, global outreach challenge, and Know Your Summit. If you have missed the 2021 Powering the Future Summit, so we have this year as well a Powering the Future Summit with the theme of digitalization in power and energy. The tentative date for this event will be on the 5th and 6th, 12th, 13th November 2022, which chose the weekends to make sure to ensure the availability of our targeted audience, which are who are YP community, graduates, student members, final year and pre-final year students, and the professional community. And we have many more programs to help you to grow your career and keep you technically up to date. We have technical webinars organized by our professional and educational activity subcommittees, as you see on the left hand side, with the title of Utility Scale Energy Storage Systems. We have a mentorship program, she for her, we will talk about it later on, and a talk show, YPFM and other activities. This is our Facebook page, so you can visit it and see our events and get the update. So we have started with the phase 1 from January to April 2022. These some photos from the graduation day. So, and some first certificates. This program gives the opportunity to young professionals and the students either to be a mentor or be a mentee, and the both experience is really good. And you will learn a lot from it. So there is a phase 2 for this program, one-to-one mentorship program. Now in the phase 2, the process is extended to 10 members, so 10 mentee and 10 mentors. And the focus area will not limit it to marketing, trend, leadership in different sector, design thinking, artificial intelligence, machine learning, digital technology, idea to paper to product, power systems, renewable energy, and professional development, and many more. So the expected outcome, professional development for those who will be mentors and mentees, learning, collaboration, growth, and contribution in energy sector. So those will be discussing and share knowledge and experience, introducing various opportunity and how you can achieve it. This will be on each Saturday, first Saturday of every month at 1 p.m. UTC. So keep the date and try to participate. There is also industry bootcamp for the final year student YPs, which have experienced from 1 to 5 years. So the area of focus will be digitalization in energy sector, software tools, power system studies. You will
just like the mute button, just like press that.
Sorry. Okay, the expected outcome, industry exposure, learning, and the professional development, understanding the research methodology. This will be for 5 days on June 2022. We have participated as well in the PS Day activities. We dedicated a special episode for PS Day celebration on the 2nd of April. It was organized by Ajis Gobi, chair of IEEE PS Kerala chapter, and joint chief technical manager heading technical consultancy.
John, can I suck your dick? Aymen, can I suck your fat dick?
Sorry?
I want to suck your penis. Don't mute me. Let me
Hello?
suck your penis.
Hello?
He wants to suck your dick.
Do you hear me?
We hear you.
Yes, wait. It's the
Yeah, I'll read.
I will
I'll
fix
read.
it.
Focus area, not limited to.
Sorry, can you repeat?
Don't worry, Ayman, I will fix it. You can continue.
Do you see my screen?
Yes.
Yes, we see.
Okay, let's continue. Okay, so the second activity is related to PSD. It's life member panel. This panel discussion between life members and students and YPs on how to manage their careers and take advantage of their technical professional organization that IEEE is to build their skill set continually in a sustainable way. In this panel session was even the president of IEEE PS was from the panelist. Yesterday we had a virtual industrial visit with
so basically, if Mbappe joins Real Madrid, his career will be finished because Mbappe is really.
Sorry. This is an insightful experience to understand the internal working environment of the company. As you know, Schneider Electrical is a multinational company providing energy and automation and digital solution for efficiency and sustainability. As you know, PS also supporting those programs, IEEE Smart Grid, IEEE Smart Cities, and IEEE Smart Village. There is everything you need in one page, which is the resources center, IEEEPS.org. So this library in the world give you access to magazine, tutorial, achieved webinar, conferences. We have our newsletter. We issue every month. So you will find in this newsletter all our activities and our future activities. We have a program of funding to encourage all PS young professional group to plan and execute initiatives to utilize the benefits of IEEE PS YP membership. So if you have any idea of event, please feel free to submit your proposal on our website, and you can get funding to sponsor your event. And in addition to PS awards, technical community awards, PS follows award, society level awards, we have set 4 awards, for 1 award for each region. So this will be in the end of the year. Below, Ainora Mahmoudova from the Region 8 being titled as a star ambassador of Powering the Future Summit 2022. and you can be the future star ambassador for powering the Future Summit 2022. This is our Facebook page, so please go and see our pages and follow us. That's all for today. Thank you for your attention. This is my email. If you need anything, feel free to contact me, and I'm here for your question.
Thank you, Mr.
Any
Aymen.
question? Thank you. Is there any question? Okay, thank you very much. And I hope to see you again.
Thank you.
Thank you so much, Mr. Aymen, for joining us today and for this informative session. We hope to see you with us in other events, and thank you so much.
Thank you, Taha.
So, do you hear me?
Okay. I hope you are spending good time with us, and have a good day.
Thank you, everyone.
Thank you. Bye-bye.